Howdy, I'm Connor Burke from Exceltex, and I'm also going to jump on the bandwagon that Jim and Dobius did and not say my actual titles, but essentially I'm just an antenna guy. I'm an RF guy. So to kick that off, we're going to do a quick quote to kind of get us in the mindset of what we're going to be looking at in regards to client AP power mismatch. So there's a quote from somebody that says, "It all comes back to the antenna." I'm not sure who that Carter guy is. I think he's some old retired guy, but we don't need to worry about him. For power mismatch, it's a thing that we often talk about in wireless. We often say, oh, well, we need to consider the AP client power mismatch. And everyone goes, oh, yeah, we need to consider that. But I feel like there's a pretty good misunderstanding of what actually causes it and what effect it has in your environment. So we're going to kind of go through the details of that and how it actually occurs. So starting off, we're going to look at the actual ERP value. So this is what we're going to look at to see what actually controls the ERP value and what your radiated power is. So depending on what device you're using, you're actually pretty limited in what you can affect in this equation. If you're using an iPhone or any client device typically, or most of the internal APs, you don't have any cable to change. You don't have any antennas that you can change. The only thing in this equation that you can change is that transmit power, and it is just the transmit output power. Now, if you're using an external AP that has antennas that you can change and swap and add cables to, you have the full equation that you can kind of play around with to adjust. And you'll see there at the end that antenna gain specifically is a bidirectional increase as you adjust it, whereas the transmit power is just the transmit increase. And we'll kind of go into how that affects it and how it can improve this or limit this problem later on. So here in the EU, these are just the regulatory restrictions that y'all have across all the different frequency bands. You can see it's roughly the same between the actual transmitter device and the client device, except for the client side, you do have that extra little bit of a limitation for LPI in the 6 gigahertz spectrum. So you would think, well, okay, if the ranges that I can play with are roughly the same for these, why do I have this mismatch? And that's because in almost all cases, unless you're doing like a point-to-point solution, your client device is never going to be even close to that ERP level. And there's a bunch of reasons for that. Predominantly, the ones that are going to control that are it's just not practical for the client device to be able to broadcast at full power the whole time. They're typically smaller devices. They have a battery life, and that would dramatically drain them versus doing it at these lower broadcast levels. And these are the internals, comparison between, this is like an Aruba 735, it's roughly 4 to 5 dBi on its antennas, but your standard client antenna is only -3 to -15 dBi, so significantly less. So that off the bat is going to dramatically reduce the RP that your client device is actually outputting. So this is where the actual mismatch comes from, is having to balance these two things. So now that we know where it comes from, we kind of want to look at how do we actually see this. So in all of our Ekahau's, Minas, Sidoses, NetAllies, when we go through and do a survey, when you have your tool out there and you're reading it, you're not reading what the AP is hearing the client at, you're reading what the client is hearing the AP at. And there's a bunch of reasons for that. It's a little bit more consistent, reading it off the Sidekick or the Nomad to see what the actual red RSSI values at that spot. But that doesn't really tell us well, what's causing this issue on the client side. It just shows us what's being heard at that area. So we can't really look at these tools and say, well, okay, I know what my client or what the AP is going to be hearing this specific client device at. We do have offsets for these that can kind of help you. I know there is a pretty big debate of whether you should design with or without offsets. I'm not going to jump in on that at this time to try to go one way or the other, but they do help you at least look at both sides of the equation. You can see, okay, I need to design my network as how it's actually measured, and then you can also go back and verify and check, well, what does it look like if I were to say I have a 10 dBi offset for a phone. So it's important to look at both, but I'm not going to take a side right now. So if we can't find it by using these tools, what do we do? How can we actually get this information to be able to see the problem and see how to address it? The easiest way and the most universal way is you can either do a packet capture with a device that has .11k enabled, or you can just grab a dump from your back end. Or some vendors have specific tools that let you see this information. Juniper has the Marvis client that actually lets you go in and see the live RSSI values as seen by the AP of what it's hearing from the client. So that's a good live view. When we go into the more practical portion of this, we're going to be looking at the dump logs because that's more universal. And as you can see there in the bottom right that's circled, the received data rates or the received RSSI values that you're seeing, it actually splits it up into the individual data streams or spatial streams rather. So it's a lot more granular being able to split it up like that. So now we know what it is and how to find it, but what does it matter? Well, why do I care about this? How does it affect my network? The biggest concern that you see and the biggest problem that this causes is a range asymmetry between your client and the transmitting AP. So your AP can be screaming at full blast, it can be broadcasting, you can be 300 feet away from it, and it is heard at the client side, but your little old client is broadcasting back very quietly and the AP actually can't hear it. So that's typically what the main issue is in this. But there's other ones besides that, so obviously the coverage issue, like we said. But if you have older devices that don't have .11k and .11r enabled, you can have a lot of roaming issues, and that's typically more common in warehouses. You can also see that causing load imbalances of them sticking to a certain AP because it's still hearing it at such a high RSSI value, but it itself is not talking back, so it doesn't want to roam. A lot of times this causes interference, not because of the innate aspects of the APs, but just people try to offset this by just cranking up the transmit power level and saying, oh, well, it'll work. The client device will be able to talk back better if I just crank up my AP transmit level. So that causes a lot of problems in the environment. And then the client battery life, as we kind of mentioned earlier, even though they aren't going to be broadcasting at full blast, they will attempt to try to push out a little bit more power to stay connected to an AP longer if it's starting to drop off from it. So it can be detrimental to the battery life of any client devices that you have on your network. A lot of people say that RM fixes a lot of this, and that can be true if your network is designed properly, if you have a high enough density of APs, to where it can actually adjust the transmit ranges properly to where you aren't having a dramatic offset between the transmit power and the actual client radiated power. But a coined phrase that I always say is that good software cannot fix bad hardware. So if you design the network poorly on the physical side, no matter what you go in and set your controller to or any of the AP settings, it's not going to be able to fix it on that end. So what can we do to actually fix this? There's a couple ways, but the way that I'm going to start off with is the antenna side of it, obviously the antenna guy. So using a higher gain antenna, as we mentioned, is a bidirectional increase. If you imagine it, it's almost like a megaphone. The AP is not only talking louder with the higher gain antenna, but it's also putting it up to its ear and it's hearing better. So it can hear the lower client device at a farther distance because it's able to hear better with that higher gain antenna, even at the same ERP. You can also, again, go back and design to have maybe a higher density of APs in an area to where you lower down the transmit powers. The client devices don't get as far away from the APs. But we're going to stick with the antenna side because that's something that we can more affect and is typically a little bit more cost effective. So going on to the practical portion of this. So we'll do a quick breakdown of the setup we use this to do for this. I just did this out in a park near our office space. The distances and the height of the pole were the same for everything. 50 meters away, that was primarily because that was the farthest distance I could get with the control group that we'll look at, so that's why we set that. Same channel, same 4x4 spatial streams. We did swap APs, but the 4x4 is really what matters there. And also, if you've never done this before, this is actually a great use for the WLAN-PI. It has a thing called bridge mode. It's not talked about too often, but if you have the WLAN-PI and an Android device and some sort of power, whether that be like an Exceltex battery pack or some other form of power, you can set up a whole AP on a stick kit like this and still have access to your AP if it's cloud managed. So in this case, I have missed APs up on my AP on the stick, and I can still go in, change all the configs, change what channel it's on, change the transmit power. So it's really easy to go out on site and actually do AP on the sticks with this. So if you haven't tried it, I would try it. The last thing I'll point out is that we're going to test all these at the same 23 dBm EIRP And I point that out as it's the ERP and the forced spatial streams earlier because I did slightly mislead y'all. The equation that I gave earlier is not the full equation for ERP. There is a final portion for that. That's the MIMO gain that we're not considering. So in this case, we're using the four spatial stream APs, so we have to do the MIMO calculation, which in this case is about 6 dBi of additional gain that we have to account for. So when you see later on the stats of what the transmit powers are set to and what the antennas are, they'll only add up to 17, but that's because we have to account for the MIMO gain as well. So how are we actually going to measure this? So as we mentioned earlier, there's a ton of great tools out there that you can do for site surveys to see what it is hearing at that specific spot. But looking the other way, these don't associate with the access point. So we can't go in and do a packet capture to see what the AP is hearing them at or get a dump log. So instead, we're going to be using 4 kind of typical client devices that you'll see. And again, these were in the same position for all these tests. So just a new iPhone, and an iPad tablet, a Pixel, and a laptop. So this is the first test that I did. It was the control test. So this is just a standard AP33, again, the 4 spatial stream AP. You can see all the stats for it up there at the top. And we can see here that it's showing the AP to client RSSI. This is what we typically see. And then this here is what we got from that dump log of what the client is hearing the AP at. And that's the average across the 4 spatial streams. And then what we'll pay attention to here is this delta value, the delta RSSI between the two. So the AP is hearing the client at an 8 dB lower RSSI value than the client is hearing the AP at. And that's pretty even across the board for these other ones. This goes down to 10. And then obviously the laptop is a little bit higher power. It has probably a little bit higher ERP that it's actually broadcasting at. So it's actually at 4 right now. We'll also point out the downlink and uplink. This doesn't become too much of a factor, as you'll see in a minute. But the first test that I did was a very low gain patch. So this patch antenna is actually at a lower gain than the Omni that's inside of like the AP33. But even with that, the directionality actually significantly improved this already off the bat. You can see the deltas all went down pretty significantly already. Remember, every 3 dB that you change is half or double. And the up and down link significantly improved, along with just the base RSSI values improving themselves. So already good improvements on using a directional antenna that's even slightly lower gain. Moving up to a median gain patch, so this is a 7 dBi patch, so again, dropping that transmit power level down on the AP, but increasing the antenna gain. We can see that the RSSI values say roughly the same on the delta, but it dropped a little bit on the pixel even. But the overall RSSI improved. And again, you'll notice that the up and down link are the same as the last test. This was more on me. So the one downside to using that setup that I was showing before of the AP on a SIG test with the WLPC, and I had not really realized this until doing this test, is that's the limit. That's your up and down link limit, is that 14 dBi. So I plan to go back and do this test with a cradle point backhaul potentially in the future to see the real results for it and or use the WLPC in the iPerf server format. So I'm not throttled at all by that, but this isn't as much of a concern right now as the delta between the RSSI values that we're looking at. And finally, we used a very high gain patch. So this is a 12 dBi, 20 by 20 roughly patch you would use for like a stadium or a point-to-point solution. Significantly dropped transmit power level. But heard very well at all the clients and very, very small deltas between all of these. One thing that you may have noticed across all these is the iPad was always a little bit higher, which you would typically think that would have a better value. I believe that's because when I had this set up, I had my iPad on its kickstand, so it was up at a 45-degree angle. I believe that the polarizations of the antennas in the iPad did not like that, but I wanted to keep it consistent across all the tests. So I didn't change that for this one, but if you're wondering why that was the case, that's likely why. So what are the key takeaways that we're seeing from having the higher gain antennas to help with transmit power mismatch? One, we do need to consider it, especially on the fringes of our networks. A lot of times when we're designing for secondary coverage, it's not going to be too much of an issue, hopefully, if you have .11k and .11r enabled. But as you get to the fringes of those coverage and or you're doing just a single cell of coverage, you're not having too much secondary, which is pretty common in a warehouse environment. This will definitely come into more play and you need to start considering it. The other takeaway that we need to consider is that the higher gain antennas do significantly impact this and reduce the overall influence of power mismatch. So I will go out on a limb and say, don't design with offsets in your predictive software if you're using external antennas. And the last thing is that I just need to try this with a better backhaul and come back to y'all next year, hopefully with a better result on the up and down link, and then hopefully with some standard power 6 gigahertz results as well. Thank you.